So for Chapter 3, Part 2, we're going to explore the first law of thermodynamics more precisely. So as I say here, energy is conserved when converted from one form into another. Energy cannot be created or destroyed. Both of these sentences are versions of what is meant by the first law of thermodynamics. So the capital E is really encapsulating all the possible types of energy you could be discussing. And so when we say all the energy in the universe, that's going to be arbitrarily partitioned into different places where that energy is. And as a chemist, we're often talking about a system and then everything else in the universe being the surroundings. If the first law of thermodynamics says that the energy of the universe is constant, then the sum of any changes between the system and surroundings must be equal to zero. That is, any scrap of energy that enters the system came from the surroundings. Now notice that we choose plus signs and minus signs kind of arbitrarily. We kind of look at the system as sort of a reservoir of energy. And if it gives off energy, it's losing energy. If it takes in energy, it's gaining energy. As I said, in chemistry, we're normally interested in the system. Now usually the chemical system that you're writing a balanced reaction for. But often, I think, in terms of a picture in our mind, you might want to think of the solution that's inside a beaker, for example, to put a picture on it. When we talk about a chemical system, we can discuss the internal energy, and our textbook uses the capital letter U for that. Remember, you don't say that the system contains heat or work, it contains internal energy. Internal energy of a system is connected to what are called parameters of state, the temperature, pressure, volume, things we've discussed already. Other types of energy could be used for the system, sort of potential and kinetic energy that are connected to the position of that system as a whole. But usually in chemistry, we're talking about systems at rest. So what does the internal energy of a system at rest consist of? Now, again, you have to be careful with the language here. When I say at rest, it doesn't mean nothing's moving, because look at some of these examples here, things we've discussed recently with gases. Translation, vibration, rotation, electronic, nuclear energy, intermolecular forces. All of those can be applied or encapsulated in what we mean by internal energy. So if you're comparing a system at one time to another, you could look at the difference in energy between those two systems. As we said, we can transfer into or outer of a system in a variety of modes. Almost always in chemistry, we're talking about heat and work. Now, there will be cases later on when you might talk about electrochemistry, but for now, heat and work are the ways to think about this. Infinitesimal changes are indicated by the lowercase d. One thing I learned in looking up the notation for equation 3.7 is that when you see that crosshatch on top of the d, that means it's an inexact differential, or another way of saying that these things are path dependent. Whereas the du here means it's an exact differential. So we'll get more into the calculus version of what that means later on. So a straightforward application of equation 3.6, this is delta U is equal to Q plus W, is a irreversible expansion against constant pressure. That's a really fancy name attached to the example we mentioned at the beginning of the chapter, when you have a compressed gas pushing against an applied external pressure. We had an equation for that. The work that's done by the system is equal to minus P external times delta V. Now, if that's the work, you could substitute it into this internal energy equation and yield this. An expansion of the compressed gas means that delta V is positive. And so therefore, the term contributes to the decreasing of the internal energy of the system. Now this is important. If the system is able to absorb heat energy from the surroundings, then that process will have a positive value of Q, which can also contribute to the change in the internal energy. An important outcome of this is what we will call an isothermal expansion. An isothermal expansion means that the temperature of the gas hasn't changed. If it's an ideal gas, delta U is precisely 0. Here's what I mean by that. If, for example, you have an ideal gas and it expands and therefore it loses some energy by doing work, suddenly that gas will be colder because it's lost some internal energy. If heat energy is allowed to flow in, these are exactly going to balance each other in the case of a ideal gas, because an ideal gas doesn't care if it's compressed or not compressed. As long as the temperature is the same, as we discussed, the kinetic energy of the molecules is going to be the same. So for an isothermal irreversible expansion against constant pressure, we see that the internal energy is 0. Work was done, that's a negative value, but heat was absorbed, and that's positive. We'll talk more about examples of this as we go on. A bomb calorimeter is something that we discussed in Gen Chem and you'll be doing in lab. A bomb calorimeter is an example of an adiabatic system. Adiabatic meaning there's no exchange of heat energy with the surroundings. It was kind of not at all like the example I just showed you. There's usually an insulation involved. Now, inside, a chemical reaction can generate heat energy, and that's exactly what you see. The heat energy can't be given off to the surroundings. It's sort of kept inside in the bomb. The thing about a bomb calorimeter is because it's sealed, let's say the reaction is like a combustion, like you're using a bomb calorimeter to see how much a cup of Cheerios, how many calories are in a cup of Cheerios. If you're producing gas molecules, they can't do any work because they're stuck inside a sealed container. So that term goes away, and any internal energy that's generated by the chemical reaction is going to be some positive value of heat energy. You see how I put that little V as a subscript in there? That's to indicate that this process was done in a constant volume environment. So the change in the internal energy in a bomb calorimeter is exactly equal to the heat that was generated. Now, as I say here, this is not a contradiction of the definition of a state function, because here we have exactly defined the path of the process. So although I mentioned the bomb calorimeter, and it's something that in chemistry, we know about, it's really kind of a specialty application. In general, in an open atmosphere, changes in internal energy are going to involve heat and work exchanges, right? Now we've got an expression for work. Usually in chemistry, it's because you're producing gas molecules or you're consuming gas molecules. So PV work is the most common form of work in a chemistry experiment. Now, since it's in an open atmosphere, whatever the pressure is that day can be defined as the state you're in, and so any heat transfer is going to be a constant pressure heat exchange. Now, just a little bit of definitions here. I rewrote this with what delta U means. It means final minus initial. That's why we always have 2 minus 1. And then I've got the final minus initial volume. Well, if you rearrange a bit, you get an expression for the heat exchange in a constant pressure environment. It's going to be the difference between these two terms, the difference between this state 2 and this state 1. That's equation 3.9. So keeping that red equation 3.9 on the side, this gives us the opportunity to define a Newt state function. This happens a lot in chemistry. You basically create a term that's going to allow you to understand something a little bit better later on, and we'll see that in a minute. So if you define the function H, or enthalpy, as U plus PV, just raw total values, even though we never calculate an absolute value of U, or we never calculate an absolute value of H, or I should say measure, we're always looking at differences. So apply the delta to both sides of this equation. And what you get is delta H is equal to the difference between these terms, the state 2 and state 1. Well, that should look familiar to you because we just did it above in equation 3.9. So by defining enthalpy the way we did, we've defined changes in enthalpy as the heat transfer in a constant pressure process. Again, This isn't a contradiction with state and non-state functions because we've defined a specific path. It's an amount of heat equated to a specific path. Now, in general, the absolute most general kind of example, so we talked about bomb calorimeters, we've talked about doing something in an open atmosphere. If you want to have an equation that is completely general, that allows pressure or volume to change, you would have this longish term here. Delta H would have 4 contributions to it. The last one is not necessarily negligible, like we did with the little d's, little p's we had, because those are infinitesimal changes. But it should be stated that most reactions that you're doing in a chemistry lab is usually on a benchtop, and it is at constant pressure. So if you are at constant pressure, 2 of those terms go away, and you end up having equation 312. That changes in enthalpy is the change in internal energy plus PdV. Another way you could think of it is minus the work. You could also re-express this in terms of infinitesimal changes. So let's look at an example of a normal everyday chemical process and compare delta U and delta H. So these values are going to differ because they refer to different quantities that were invented essentially to highlight different conditions. And I hope this will make this clear. So imagine we're going to take some sodium. This seems fun. 2 moles of sodium and put it in 2 moles of water. You're going to get a lot of heat, 367.5 kilojoules of heat. The sodium hydroxide will be in solution, and you're going to produce lots and lots of bubbles of gas. If you did this open to the air, the heat that's generated is QP, because it's constant pressure conditions. Now, QP is equal to delta H, as we've said, minus 367.5 kilojoules. That's the change in the enthalpy. If you want to calculate the change in the internal energy, you use equation 312, which states that delta U is delta H minus P delta V. Now, assuming that the solution's volume isn't changing very much, it's probably changing a tiny bit in some way. I really should say the volume of the condensed phases aren't going to be changing a lot. We're going to assume that the bulk of any volume change here is going to be on the creation of the gas. So we can show, using standard ideal gas law, that the volume of 1 mole at room temperature is about 24.5 liters. So the second term in the internal energy equation, minus P delta V, is going to be minus 24.5 liter atmospheres. Using the conversion factor we've discussed, it's minus 2.5 kilojoules. So the change in the internal energy is going to be minus 367.5 kilojoules minus 2.5 kilojoules. The change in the internal energy is minus 370 kilojoules. Now, why are these different? Does this make sense to you why one is more negative than the other? Well, the reason that the magnitude of the delta H is smaller is that some of the internal energy that's released in the process does expansion work by pushing back on the atmosphere so less heat is evolved. So if you have basically condensed phases and you're creating, so this is my just sort of schematic diagram of the sodium and the water. So these are the condensed phases. And their volume isn't changing, but you're creating a bunch of H2 gas. You have to push against the existing atmosphere for those molecules to occupy space. So in general, the difference between delta H and delta U in reactions has to do with gases. So delta, the product of PV, is going to be delta, so we have our nRT, which is equal to RT delta N, if T is constant. So in the example above, the delta N is 1. We created 1 mole of gas. And 2.5 kilojoules is not negligible for accurate work. That said, when the reactants and products are all in the condensed phases, delta U and delta H are generally the same. When everything is solid or liquid or aqueous. All right, we have example 3.3 from the text, trying to illustrate a comparison of delta H and delta U now in a bomb calorimeter. So this looks like 0.5122 grams of naphthalene in a bomb calorimeter. Usually that's the chemical that you're going to use with Dr. Breen to standardize. That's not the word? Calibrate your bomb calorimeter. So if you take this much naphthalene, burn it in the bomb calorimeter, the change in the temperature ended up being 3.91 degrees K. If the heat capacity of the calorimeter had already been tested, actually you're going to determine the heat capacity of the calorimeter using naphthalene. But if the heat capacity of the calorimeter was already determined, that's what the CV means here, constant volume heat capacity, was 5258.8 joules per K. To have those units right? Yeah, I think so. Calculate the delta U and the delta H. Okay, first things first, you have to know the reaction that is going on in the calorimeter. The heat capacity was given and the delta T was measured, so you end up generating 20.60 kilojoules of energy. Now that's heat energy in a constant volume process. That means that's what the delta U is. If you want to figure out how much energy is generated per mole of chemical, you want to take the amount of heat energy that you measured and then figure out how many moles of the naphthalene burned, and so you're getting 5156 kilojoules of heat energy for every mole. Now, what about the delta H? Now, as we said, delta H was invented to calculate heat transfer in constant pressure environments. So it's kind of not, it's using a tool in the wrong context, but it still can be calculated. To get the delta H, you need the delta U plus delta PV. And we do a little substitution in here as we did, assuming ideal gas-ish behavior. Delta N, the change in the moles of gas, is a -2 because you're going from 12 moles of oxygen to 10 moles of CO2. So if delta N is -2 and you substitute, you get minus 5161 kilojoules per mole. So it's pretty close to the delta U. Why is that? I have some notes here. Notice that delta U's and delta H's are virtually the same in constant pressure environments or constant volume environments. Q, however, is a little bit different because it is path dependent. We ignored heat capacities of the products and any excess oxygen. Those aren't really big errors. Note that you get a little bit more heat out of the constant pressure process because the atmosphere is doing some work in the system. Is that clear? So if you did this reaction to open air, the volume would actually be less after the reaction because 12 moles of oxygen are going to occupy a certain volume, and then since you're only producing 10, the surroundings is doing some work on the system, which, as I said, is going to actually make the enthalpy value a little bit larger than the internal energy value. Take a look at example 3.4 on your own, and I think I'll have to have a third video for section 3.4, although I'll have to save that for probably later this afternoon.